Okay, folks, can you hear me okay?
Yeah.
Okay. Sorry, I had some little technical issues there. Had the wrong wireless network. There's so many things that can go wrong to do when we do this. Okay, so I guess it's time to start. The plan for today is to let me get this. The plan for today is to discuss our Slater Determinant and exchange forces. And you guys can hear me okay, right?
Yeah.
Okay. All right. So let's just start where we left off last time. Sorry, my computer's a little screwed up here. Okay. So last time we were talking about many body systems. And it's basically the quantum mechanics of multiple particles. And so the idea then is that if I have a box, and I know that if I have multiple states in the box for a single particle, then where these are states A, B, and C, then if I, for example, if I put three particles, sort of a normal many body state of three particles, for three particles would be to just stick them in there in any way you want. Let's say I put one in state A, one in state B, one in state C. And so then I could just say that the many-body state of these three particles is just going to be then the product state of particle 1 is living in state A, particle 2 is living in state B, and particle 3 is living in state 3. So it's a product state. So that's the normal. Please mute please mute yourself. The product state is the normal many-body state. And okay, so that's an important thing just to kind of understand. That's like the starting point. But then the idea is that if we have indistinguishable particles, then when we take a close look at that, then something interesting happens. And we discussed that last time, so I'm not going to go through it all again. I'm just going to remind you that if we have indistinguishable particles, then what happens is if the particles are all the same and they each have a spin that is an integer spin, then what we have is that they're called bosons. And then the property of bosons is that if I take the many-body wave function of a system of bosons, and if I hit it with the exchange operator, that exchanges any two particles, the labels of the particles on the wave function, the I and j particles, then that gives me the same wave function back again. And that means that and so that type of state we call it a symmetric state. So then so we say that the many-body wave functions of bosons have to be symmetric. They're eigenstates of the exchange operator with the eigenvalue of +1. Whereas on the other hand, if the spin of the particles is half integer, then what we call those particles are fermions, and they have the property that if I hit their many-body wave function with the exchange operator, then I get back the same many-body wave function, except it's multiplied by -1. And so that is a property that we call antisymmetric. So we say that the many-body wave function of fermions is antisymmetric. And when we use that word, what we mean is it's antisymmetric under the operation of particle exchange, which means just swapping the labels of any two particles in the wave function. All right, so that's a property that particles have. And so then the question is, how do we construct these special many-body wave functions for indistinguishable particles? for indistinguishable particles, systems of indistinguishable particles. How do we construct these wave functions? And so this is sort of where we left off last time. And the answer is that there's a trick. There's a math trick. And the idea behind the math trick is that to construct the many-body wave function, it's going to be equal to a linear superposition of product states. Because the idea is that it's like back here when we're throwing in these three particles into this box, we could have said that this is particle 1, this is particle 2, this is particle 3, or we could have said that this is particle 3, this is particle 1, and this is particle 2. We can change the labels in the product states, and so there's all these different product states that we could have, and we have to create a linear superposition of all of those product states, and that's how you do it. But that's kind of complicated, and so what? I'm sorry. And so it turns out that there's the math trick is to use a Slater determinant. And so now we're going to talk about the Slater determinant. This is the math trick to construct the many-body wave function for indistinguishable particles. It has a well-defined symmetry with well-defined symmetry. And the symmetry here is the symmetry with respect to particle exchange. So let's talk about the Slater determinant now. So the Slater determinant can be written like this. I'm going to write. So this is, so if we have n indistinguishable particles, and we want to put them, and they're living inside of some, and let's say that they're living inside of some box, some Hamiltonian, the landscape, and this box has a bunch of states. Let's just label them A, B, C. There's a whole infinite number up to C. Just a bunch of states. Then to construct the wave function, then to make the wave function, then you have to put the particles into the box. Put particles into box. But there's many different ways that you can do it. And your wave function has to reflect all the different ways that you could do it in order to construct the correct symmetrized wave function. And so the way you do it is like this. The wave function then, the many-body wave function, which is going to be a wave function of particles 1, 2, and I have n particles. Then the wave function, that wave function, the physical wave function is going to be a constant. This is the normalization constant times this. This is a determinant, and it's this big determinant. And this is, if you've never seen this before, it's kind of weird. The first time you see it, it's kind of weird. But I just want to say, this is actually used a lot. I'm telling you now something really important. If you've never seen it before, it's a little bit weird, but it's very important. We construct a determinant, and the determinant in the top row, we take the 8th state of particle 1. Then the next element is the 8th state of particle 2, and then all the way to the 8th state of particle n. And then the next row, we look at the next state of particle 1, the next state of particle 2, state B of particle n. And then we go all the way down to the very final state that's occupied, Xi, some arbitrary state of particle 1, Xi of particle 2, and state Xi of particle n. And this is a determinant. And so basically what we've done is, you can see that in the vertical direction, we're it's an n by n determinant, n by n determinant. And you can see that in the vertical direction, we're indexing the states. And in the horizontal direction, we're indexing the particles. Okay, so in the vertical direction, so basically the idea is that we're just throwing the particles into the box, into all the different states, and all the different states that we throw the particles into, we index by the rows. But all the different particles, which is particle 1, particle 2, particle 3 to particle n, we're indexing via the columns of this determinant. And this is so this is a function, because the determinant, if you do all the operation of the determinant, you get a big gigantic function, and this function gives you the proper symmetrization. So this is actually used a lot in quantum mechanics. And so, but the normalization constant is tricky. For fermions, then the normalization constant is easy. It's just 1 over square root of n factorial. But for bosons, it's trickier. Then the normalization constant is 1 over square root of big N factorial times little n A factorial, little n B factorial, little n C factorial, etc. Where NA equals number of particles in state A, and NB equals number of particles in state B, etc. And so this is a math trick. And now let's take a look at this. And so,
Professor?
yeah.
So will NA, NB, and C be the same?
Yeah, it depends. Like, suppose that I had 3 particles in state A.
Oh, okay.
Then what I would have 3 rows that are psi A of x1, psi A of x2, psi A of x3, and then I'd have another row, psi A of x1, psi A of x2, psi A of x3, and then another row, psi A of, because because those are the states. All right. And the best way is to sort of do examples, This is one of those things where if I try to like write down the general conditions of this, it just becomes quite tedious. But if you just do it and play around with it, then you see that it's actually not so hard. It seems hard when you first see it because it's so weird looking, but after you mess around with it, you realize it's not so bad. Okay, so let's talk. Yeah.
Another question. So for the Slater determinant, doesn't it only work if we have equal numbers of states and particles?
Well, no, it'll work. I mean, it'll work just fine because it depends whether you have fermions or bosons. First, I just want to say that the box typically has an infinite number of states, right? All the eigenstates is typically infinite. And if you the 2 situations are different depending on whether you're talking about fermions or bosons. So let's talk about those right now. And then I think that might help answer your question. So let's talk about fermions. For fermions, there's 2 things to notice. There's something really nice to notice, which is that so for fermions, first I just want to say, actually, let me let's just say for fermions, actually I want to write it a little differently on my screen here so I can write everything down. For fermions, then what happens is we calculate the determinant in the normal way. Okay, so it's just a normal determinant, and you guys have all done that in your linear algebra class. You know how you do determinants, you do the diagonal, and you cross multiply in all those different ways. And remember, for determinants, you go plus, minus, and you add all these negative signs. Yeah, no, you've all done that. So for fermions, you calculate the determinant in the normal way. And then there's two things to notice. The first thing to notice is that when I look at this determinant, if I consider a particle exchange of, say, if I consider the particle exchange operator, then if I hit the wave function with the particle exchange operator, what does that correspond to for the determinant? If I was to swap labels for two particles, then what mathematical operation does that correspond to for my determinant? Now I'm asking you a question. Somebody answer that question.
Is that a row operation?
What do you mean a row operation?
Never mind. I'm thinking about it wrong.
So look at this determinant, and if I swap the labels of any two particles, what does that correspond to doing to my determinant? Tell me, someone.
Are you exchanging columns?
Yes. Swap labels is the same as column exchange. And I want you to stare at that and see. It's like this, because if I was to have, if I was to say P12, then I'm exchanging columns 1 and 2. I'm swapping them. Badoop, badoop, badoop. Okay. And if I swap two columns in a determinant, then what does that do? It's a property of linear algebra. If I swap two columns in a determinant, what does that do?
Just make it negative.
Yeah, it makes it negative. And so immediately you can see that the determinant automatically gives you the proper symmetry, because if you swap the labels of any two particles, it goes to the negative. Isn't that beautiful? It just works. See, that's so clever. So that's how you get the automatic anti-symmetrization. And so it makes negative, so then you get it's anti-symmetric. The determinant is anti-symmetric. And then there's something else to notice, which is really important. Suppose I have two states are the same. If two states are the same, then that means that two rows are the same. Can you see that? If I'm throwing the particles into the same state twice, that means that in my Slater determinant, two rows have to be the same. That's how you construct the Slater determinant, because every state that you throw the particle into is one of the rows. So if two particles go into the same state, then that means that two rows of my determinant are the same. All right, I want you to see that. I hope that makes sense. And now I'm going to ask you the question. The question is, what happens to a determinant when two rows are the same for any determinant? This is a linear algebra question.
Does it go to 0?
Yes, it has to. That's a property of linear algebra. Then the determinant equals 0. And that is an expression of the idea that if I put two particles in the same state, I cannot anti-symmetrize that wave function, because if I exchange those two particles, the wave function goes to itself. If two particles are in the same state, then in the product, well, you guys play with it yourself and you know, work on that. And I want you to think about that until you convince yourself that it's true. If two particles are in the same state, then I cannot anti-symmetrize the product, or even a superposition of products. And so what happens is that there is no, the wave function goes to 0, which means that it's not physical. And that's just another word for saying that it doesn't happen. You cannot construct a wave function, an antisymmetric wave function, where two particles are in the same state. And you can see that immediately from this Slater determinant. It just jumps right out at you. And so what do we call that? We have a name for that. What
Pauli exclusion?
Exactly. That is the Pauli exclusion principle. And I know that you all have heard of this before. And you all have heard of this idea. Maybe some of you haven't, and now you're feeling embarrassed, but that's okay. You know, you don't. I won't out you. So the Pauli exclusion principle, that is the Pauli exclusion principle, which is that no two particles can be, no two fermions can be in the same state. No two fermions in same state. Now, I know that like 99% of you have heard of this before, but you never really understood it until now, hopefully. This is where it really comes from. This concept of the Pauli exclusion principle is a manifestation of the anti-symmetrization of the fermionic many-body wave function, because you cannot anti-symmetrize a many-body fermionic wave function if two particles are in the same state. And that means that two fermions can never be in the same state. That's where the Pauli exclusion principle comes from, okay? So I just want you to see that, and you can, and it's sort of, it's a cute thing. Okay, so now let's consider bosons. And so for bosons, we have this, it's tough because of this stupid, you know, iPad, I can't show everything at the same time, but for bosons, you see we have that same wave function, that same determinant, but we have a slightly different normalization factor for bosons. And the idea for bosons, in order to calculate the wave function for bosons, what happens is you calculate you calculate the determinant, but there's a trick. You know how when you calculate a determinant, you insert all those minus signs to calculate the determinant? For the bosons, you take all the minus signs and you convert them into plus signs. So no, you don't add all the minus signs. No added minus signs. Okay, so it's not really a determinant anymore, but you calculate the same way you would a determinant, but you don't do that minus sign trick. So it's not really officially a determinant anymore. And so what that means is that that trick, that if I hit the ij on my many-body wave function, then it still is the same as swapping two columns. But now it doesn't go to its negative. All right. So when you swap the two columns, it doesn't really change anything. And you can see that if you sort of play around with it, then you can prove to yourself that that's true. Then there's no sign change. Also, now if two rows are the same, then a property of this new type of determinant, it's not really determinant, but the property of this new thing we're calculating is that it doesn't go to 0. It doesn't go to 0. So that property of the determinant, that if two rows are the same, it goes to 0, is gone. because I got rid of all those negative signs. So that no longer happens. And so now it's okay for two particles to be in the same state. Because the bosonic wave function is not antisymmetric, and it's symmetric, so it no longer has that property that if you put two particles in the same state that it goes to zero. That no longer happens. So now two particles can go in the same state. There's no Pauli exclusion principle.
Can I ask a question?
Yeah.
So is the Slater determinant the only way to construct the antisymmetric situation? Because for Pauli exclusion to be true for every situation, we need to prove the Slater determinant is the only way to construct such an antisymmetric.
No, I don't think so. I think that what you could prove instead is that if you had products, if you have an arbitrary linear superposition of product states where two particles are in the same state, that linear superposition, however you construct it, will be zero. You cannot construct it. So I think it's an easier proof. I don't think that I have to prove that the Slater determinant is unique. I just have to prove this other thing. See what I'm saying? So play around with it. Try to prove that other thing. And so you're asking, like, is it unique? I don't know. I don't know if the Slater determinant is unique. I don't think it is. I don't think it's like the unique solution. I don't really know. But we just use the Slater determinant. I mean, it's kind of what everybody uses, and it sort of brings out these properties very beautifully. But I think the properties that we're talking about are kind of more fundamental than the Slater determinant. Okay, so now let's talk about, these properties lead to statistics. So let's talk about the statistics of the many-body wave function. And so what we'll do is, people use this word statistics, and so what they mean when they say statistics is they mean the counting of the eigenstates. Let's consider the counting of the eigenstates. How do you count the eigenstates? The energy eigenstates. Counting the energy eigenstates. That when people talk about statistics, that's what they really mean. So let's count them. And so let's consider two fermions.
Professor, is it okay
Yeah.
if I ask another question about the Slater determinant before we
Sure.
move on real quick? So for the boson case, are we saying that the product, or are we saying that everything will be positive in the state?
What we're saying is that when we add up all of the linear superpositions, what we're saying is that when we add up all the product states, we will add them up only with plus signs. However, the product states themselves, the little pieces, psi A, psi B, psi C, they might have negative signs inside of them.
Okay. Okay. Thank you.
Okay. So consider two fermions, and so let's consider, and so let's put these two fermions in a box, because there's always a box, right? You got to stick them in something. And I like to draw this box, but of course the box could be an atom. It could be any Hamiltonian. I just like to draw the box because it's easiest to draw, and the physics jumps out most easily. So let's consider a box, infinite square wall box, and I have states psi A, states A, B, C, and you know what these states look like. These are the 1 half wavelength, 2 half wavelengths, etc. And so now for two fermions, let's put them in the box. And so this bottom state has energy A, this second state has energy B, that state has energy C. So what's the lowest energy state? I have two fermions in this box. What's the lowest energy state? And we're not considering spin. Right now, let's neglect spin. So if I don't think about spin, where can I throw those two fermions? So I'll ask you a question. Can I put them both here? in that bottom state?
No,
Yes or no?
because there's Pauli exclusion.
Exactly, I cannot do that. So I can, but I can put one of them there. So where should I put the second one?
In the B state.
Yes. And so then, so even without even doing a Slater determinant, what is the energy of this state? What is the energy of this state?
EA plus EB.
Exactly. One electron is in state A and one electron is in state B. That's really pretty simple, you know, just add them up. But now what is the wave function? What does the wave function look like? That's more complicated because it has to be symmetrized. So let's write down the wave function. So the wave function, which is to be a function of particle 1 and particle 2, is going to be equal to, so I have two particles, and so let's go back here. I see it's 1 over square root of n factorial, and so it's going to be 1 over, in the middle, it's going to be 1 over square root of what? What goes in here?
2.
Yeah, because 2 factorial is 2. And then I got to construct my determinant. And so the determinant is going to be the first row, the rows denote the states. And so the first state is state A, and that's with particle 1. And then I have state A with particle 2. And then the second row is going to be the second state, state B of particle 1 and state B of particle 2. So I'm just using the trick, you know, I'm constructing the Slater determinant. And now I got to calculate it. So it's going to be 1 over square root of 2. And I got to do that, you know, you do that cross multiply thing. So it's going to be psi A x1 times psi B x2 minus psi B x1 psi A x2. All right, and that's my wave function. You see, because it's two product states. So these are the two different possible product states, and now it's symmetrized, because now you can see that if I hit it with the exchange operator P12, then you see it goes to its negative. So I want you to look at it and just kind of see how if I was to exchange those labels, it would go to its negative. P1, and I'm not going to do the algebra, but P12 of psi is equal to negative psi for this many-body wave function. And also, now what we could ask is, what's the next excited state? And what's the next excited state? So here I have my states A, B, C, and so what's the next higher energy? I put one electron where? How do I construct the next state?
Put one in the C state.
Exactly, and where's the other one go?
In the B state?
Well, I could do that, but would that be the very next highest energy?
Goes in the A state.
Yeah, exactly. To be quite honest, it depends where these energy levels are, A, B, and C. But typically this is how it works. Typically, this would be then the next highest state. The energy would then be EA plus EC, and then you could construct it. You know, be 1 over square root of 2 times the Slater determinant, right? And you calculate it. I'm not going to do it, but I want you to sort of see the pattern. So now let's consider bosons. Two bosons. So let's take those same two states, but now suppose they're bosons. And so let's construct the wave function. So now I have these three states, A, B, C, and what's the, and I have two bosons, and what's the ground state? What's the lowest energy state? Is to put them where? Say it again?
Both in A. Both in A.
Yeah, because there's no Pauli exclusion principle. So I can put them both in A. Exactly. And so now the energy is equal to what? What's the
2
energy?
A.
Exactly. That's exactly right. And now I can calculate the wave, the ground, and now I can calculate the wave function. So let's calculate the manybody wave function. And then I'm going to have, if I do the normalization factor, it's going to be 1/2. And now let's do the, if I do the trick with the bosons, it's going to be, because it's going to be 1 over square root of 2 factorial times 2 is 1/2. And then I'm going to have the first state is going to be psi A of x1, psi A of x2. But then the next state is also going to be psi A of x1, psi A of x2, because I'm putting them both in the same state. So the two rows are the same, but the columns denote the two particles. So I want you to see the pattern. And so now when I multiply this out, I can go this, but instead of saying minus, I'm going to go plus. So this is going to be equal to 1/2 psi A x1 psi A x2 plus psi A x1 psi A x2. So it just means it's just going to be psi A x1 psi A x2. That's the wave function. See that? It's just a simple product state. And so that means they're both particles are sitting in the wave function. And this is a symmetrized function, because if I swap the two labels, it comes back to itself. You see that? It's symmetric. Because P12 psi equals psi. I just want you to see that. Okay, now I just want you to see that the energy of the ground state is very different. Because look, for the fermions, the lowest energy state was this. This was the ground state for the fermions. Let's go back to this earlier example. You see the lowest energy state was that. But for the bosons, the lowest energy state is that. And so that's what people mean when they say the statistics are different. The counting of the energy levels is very different. For the even though all the energy, even though we're using the same single particle wave functions, when we occupy the levels, the counting is very different. And so then we would say, what's the next excited state for the bosons?
AB.
Let's see, here's A, B, C. So one particle goes in A and the next particle goes where?
B.
Yes, exactly. And so then the next excited state will be epsilon A plus epsilon B. And now when you calculate it, psi, when you calculate it, now you're going to get 1 over square root of 2. And now you're going to get psi A x1, psi A of x2, psi B of x1, psi B of x2. And it's going to look a lot like the fermionic wave function, but not exactly, because now it's going to be 1 over square root of 2 psi A x1, psi B x2 plus, see, the other one had a minus, but now we have a plus. Now it'll be psi B x1, psi A x2. And now you can see that if I swap the labels P12 of psi, then it comes back to itself. See, look at that and just swap the labels. See, it comes back to itself. Okay, so that's the trick. That's how you do it. And so, and then of course you can just go on and on and on. And so now what we're going to do is let's ask ourselves a new question. Because, see, here's the thing, check it out. I mean, all we did was we have the same states, A, B, C, and we're just occupying, you know, if we have a system of particles, a bunch of particles. We're just throwing them into the box, right? And so let's ask ourselves, is there a physical consequence to the symmetrization? Is there a physical consequence to symmetrization? Because you notice that for example, for two particles, if I just put two particles in these states, A and B, then you notice that the only thing that changes is the sign of this guy right here, right? So this is plus for bosons, and for fermions, it's a minus. We just showed that. And so what I'm asking now, is there any consequence to the sign of that? You know, like if I construct a two-particle symmetric wave function, or two-particle anti-symmetric wave function, or two-particle not even symmetrized wave function, then the question is there any is there any consequence in the physics? And so let me actually make that more explicit. So we'll take two particles in states, and we'll put them in states A and B. And we're going to consider three cases. Let's consider case one, which is the particles are distinguishable. Now, if they're distinguishable, do I need to symmetrize the many-body wave function? Yes or no?
No.
That's right. So a perfectly valid wave function would be psi of x1, x2 is equal to the product state, psi A of x1 times psi B of x2. Now I want you to look at that and realize that that's not symmetrized, right? It's not, because if I exchange the labels, it does not come back to itself. So for distinguishable particles, like if I had an electron and a muon, and I threw them into my box, this is a perfectly valid wave function, many-body wave function. But now let's consider the second case, where I have fermions. And now when I calculate the wave function, x1, x2, for two particles in those same two states. Oh, before I do that, let me just ask a question. What is the energy of this state? The energy is what?
EA plus EB.
Exactly. Because one guy is in A and one guy is in B. Now let's calculate, now let's suppose that those two particles are indistinguishable fermions. Indistinguishable fermions. Then I have 1 over square root of 2 psi A x1 psi B x2 minus psi how do I do it? Psi B x1 psi A x2. Okay, and now it's anti-symmetric. And I'm asking you, and the first thing I want to ask you, what's the energy of this? Someone tell me, what's the energy of this anti-symmetric state that I just
EA
wrote?
plus EB.
Yeah, same. It's the same energy, exactly. Same energy. Let's see, for all, same energy. And now let's consider the third case, which is indistinguishable bosons. And so now let's consider this, x1, x2. And now for bosons, it'll be 1 over square root of 2. And that's going to be the same, except that a slight difference, psi B x2 plus psi B x1 psi A x2, because now it's symmetric. What is the energy of this bosonic many-body wave function that I just wrote?
Still the same.
Yeah, still the same. Okay, so now you see it right in front of you. You got these three situations where I have two particles and I'm putting them in the same two states that have the same two energies. And the only difference is that in one case, the particles are distinguishable. In the next case, they're indistinguishable fermions. And in the next case, they're indistinguishable bosons. And so my question to you now is there a physical difference? Like, do these systems, these three systems, 1, 2, and 3, do they have any different physics? Is there any difference in the physics? Any difference in the physics? And what do you think? Yes or no? I mean, some of you might have seen this before already, so you know the answer from some previous class. But if you've never had this class before and you've never seen this before, I'm just curious what you think.
I think no.
That's a very reasonable thing to say. Yeah?
We kind of know the answer from 137A.
How do you know it from 137A?
I think last semester we did a bit of bosons and fermions. So I guess, if I remember correctly, if we calculate the expectation for positions, then we find out that bosons tend to be closer and fermions tend to be further apart.
Yeah, but I was asking for people who haven't had this course before.
Sorry.
So, because I know that some of you have seen this before. Usually in 137A, that is not covered. So, you know, usually that's not covered, but I guess your professor did cover it in 137A. So that's you know, that's unusual. Although maybe it's not. I mean, how many of you have seen this before in 137A, what I'm about to do? Could you raise your hand? I am kind of curious because raise your hands, all the people. Let me see, how do I do this? I can't remember how to check who has raised their hands. Shoot. How do I don't know how to, okay. Oh, it says 12.
Just look at our cameras.
Well, it says 14, 15, 16, 17, 18, 19, 20, 21. So, okay, everyone who has seen this before in your 137A, raise your hand. I'm kind of curious. Okay, so 25 people have raised their hands out of 56. 26. Okay, well, it looks like roughly half. Okay, so half of you have seen this and half of you have not. Okay, well, or now it's, okay, well, I don't know how to do this thing. Okay, so it looks like a good number of you have seen it, but a good number have not. All right, so well, I'll just continue. So the thing is that, oops, sorry. I'm having some little issues here. Okay, so the question is there any difference in the physics? And the answer is yes, there is a difference. And the difference is due to the fact the symmetrization causes a difference. And so this is the origin of what we use the word exchange force. We call this the origin of exchange forces. And the reason why we use this word exchange is because the difference in these particles, I'm sorry, the difference in these wave functions is that they behave differently under the process of exchange. And so that, let me get this right, I'm sorry. And so that means then that that the physics, we call this the physics, we call this like exchange physics, and we like to use the word force. And the reason why we say why we use the word force is because the particles are they behave as though there is a force between them. And the force, it's like a pseudo force. It's a fake force. There is no force. Because in this case, the particles are independent. There's no actual forces between the particles, but there's a pseudo force. I'll call it a pseudo force, meaning that they act as though a force exists. And so then, and it's purely from the symmetrization. And so we call that an exchange force. And this force is really important because this, for example, is the origin of magnetism. Because this force that we're talking about is why we have magnetism. But I'll explain that later. But right now, it's important that you see the origin of this force. And so in order to see it, what we're going to do is let's calculate the average distance between the particles, x1 minus x2. And this is the expectation value of the distance between the particles. So we're going to calculate, so this is the distance between the particles, distance between particles, and it's the quantity squared. And we have to square it because otherwise it would just average to 0. And so let me remind you of expectation value. Expectation value. You guys remember that if I have if I put a particle in some wave function psi, like that, then if I ask you for the expectation value of the position, I'm saying if I perform a measurement of the position of the particle for an ensemble of particles, then the average value of the position, average value of position is equal to, and you guys all know how to do this, you integrate psi star of x or psi of x, it doesn't matter the order, psi of x times x, well no, let's do the star here, psi star of x times x, psi of x dx. Okay, that's the expectation value. And I know that you guys have all done that before. But now, if we have a manybody wave function, like psi of x1 and x2, then now I can ask you questions like I can say, what's the average position of particle 1, x1, right? I could say, what's the average position of particle 1? And then what you would do is you would then integrate psi of x1, x2 star operator x1 times psi of x1, x2. But now you have to integrate over dx1, dx2. Okay, so this is just a generalization of a familiar concept, expectation value. So that's the average location of particle number 1. The expectation value of the x1 operator. So now if I want to figure out the average distance between two particles, then I just have to calculate the expectation value of x1 minus x2. But this will be 0. That's why I have to square it. And then if I wanted to know the distance, I would then take the square root of it. But we're not going to bother with the square root part. And but now you guys have all done expectation values before, and so let's just take a closer look at the algebra of this quantity. So it's gonna be the expectation value of x1 squared plus x2 squared minus 2x1 x2. So you see how these two things are the same. And by the algebra of expectation values, if I do all those integrals, then that's going to be the same as the expectation value of x1 squared plus the expectation value of x2 squared minus minus twice the expectation value of x1, x2. Okay, so that should look a little bit familiar. And so let's calculate this. So let's calculate this for the three cases. Calculate it for the three cases, case 1, case 2, and case 3 that I said above, where case 1 is the distinguishable particles, and case 2 is the indistinguishable fermions, and case 3 is the indistinguishable bosons. So let's do that. So let's look at case 1. Let's calculate. Now I have psi x1 x2 is equal to psi a of x1, psi b of x2, and so now I'm going to calculate the expectation value of x1 minus x2 squared, and let's calculate it. And when we calculate it, we see that what we have to do is we have to calculate these three components. And so let's do them each. And so to calculate them, let's first calculate the expectation value of the position, the expectation value of the position of particle 1 squared. And so now I just have to then integrate it twice, and I'll write here psi a of x1, psi b of x2 star x1 squared, and then psi a of x1, psi b of x2 dx1 dx2. All right, so you see that I'm just calculating this quantity, and there's some algebra associated with it, but you see I can move things around, and I can see that this is then going to be the integral from negative infinity to positive infinity of psi a of x1 star x1 squared psi a of x1 dx1 times the integral negative infinity to infinity psi b star of x2 psi b of x2 dx2. All right, so I'm just doing, this is algebra, so this is kind of tedious algebra, but it's nothing too, it's nothing fancy. And so this one right here, what's that going to be equal to?
1.
Yeah, exactly. Because wave functions are normalized. And this, and this one is kind of funny because notice that the 1 is a dummy variable, in the sense that I could have, I mean, the 1 sort of has no meaning, the number 1, because I could have put number 2 or 3, because what I'm calculating here is this is actually the expectation value of the position operator squared for the state A. So if I put, this is the same answer I would have gotten for just a single particle put in state A. It doesn't care, that it doesn't even know that it's a many-body particle. All right, and so we see then that x1 squared is just equal to x squared for state A. And then if we did the same thing similarly, if we calculate the expectation value of particle 2 squared, then we see that that would equal what? X squared in state what?
State B.
Yeah. And the reason is because you see that particle 2 is in state B. Particle 2 is in state B, whereas particle 1 is in state A. Particle 1 is in state A. Okay, and then we have to do the next part. We have to then, the next part is to calculate the expectation value of x1, x2, the product. And so now we've got to do that. And so that's ever so slightly tedious, but if we calculate it, then you can kind of see how you're going to get an integral over the position of particle 1, which will be psi a star x1, x1 psi a of x1. And then that's going to get multiplied by an integral over particle 2 psi b star of x2, x2 psi b of x2. So I skipped a step, but I just want you to see how I'm just doing the usual thing. And so now this part is equal to what?
Expectation of position in state A.
Right, the expectation value of the position operator in state A. And this guy is equal to what?
The same thing in state B.
Exactly. And so then we see that this is equal to the expectation value of the position operator in state A times the expectation in state B. So what we learned from all of this is that for the first case of no symmetrization, then the distance between the particle, or the distance squared between the two particles, is equal to this: x1 minus x2 squared is equal to the expectation value of a single particle in state A plus the expectation value of the position operator squared for a single particle in state B minus 2 times the expectation value of the position in state A times the expectation value of the position in state B. Okay, so we calculated that, and this might seem a little abstract, but I think each step is fairly straightforward. We're just grinding through the algebra. So now what we want to do is we want to calculate the exact same quantity for case 2. Now let's do the same thing for case 2, which is the case of indistinguishable fermions. And now I'll remind you that we have this this wave function now, where the wave function looks different, because now if the wave function is 1 over square root of 2 times psi a of x1 psi b of x2 times minus, now it's psi b of x1 psi a of x2. Okay, that's our wave function now. And so now we're going to calculate the same thing. So the distance between the particles is the same thing. It's equal to x1 minus x2 squared, and it's going to be the expectation value of x1 squared plus the expectation value of x2 squared minus 2 times the expectation value of x1 times x2. Okay, so we've got to calculate that same thing. So it's quite tedious actually to do this. Yes, but it's not hard. And so let's calculate it. And so let's do each one, these 3 calculations, and let's do them. And so we see then that x1 squared, the expectation value of the position of particle 1 is going to be, it's going to be, I got to set up that integral. So there's going to be 1/2 out in front, and I'm going to do 2 integrals from -infinity to infinity over position particle 1 and particle 2. And then I'm going to have the wave function, the star, so that'll be psi a star of x1 psi b star of x2 minus psi b star of x1 psi a star of x2, and then the operator x1 squared, and now the same wave function without the star, psi a of x1 psi b.
Question, Professor.
Yeah.
Would it be a good idea to write plus or minus instead of just minus? Because that way we can cover both fermions and bosons at the same time.
Sure, that would be elegant. I'm not always doing the elegant. I'm not such an elegant guy when it comes to math. But yeah, psi b of x2. But what I'm going to do is, I mean, I have it in my notes, so I'm not going to sort of change how I do it. I'm going to skip a bunch of steps. I'm not going to go through every step. I just want to set it up. I just, you know, so I'm writing the tedious algebra here, and you guys can see how to set this up. But now you have to grind through all those little integrals, multiply it all out, grind through it. And when you do all that, what you're going to find is that this quantity x1 squared is equal to 1/2 times the expectation value of the x squared operator for state A plus the expectation value of the x squared operator for state B. And then you're going to find that the expectation, and if you do the same thing for the expectation value of the particle 2 squared, it's going to be the same. And then if you do the whole, thing over again now and calculate this quantity, then if you do the same thing and now plug in the x1, x2 and do all those integrals, then what you're going to find is that you get something different. You're going to find that you're going to get that the expectation value of x1 times x2 for the fermionic wave function is going to give you this. And I'm not going to go through the algebra, but you guys can do it. It'll give you the expectation. It's the expectation value of position for state A times expectation value of position for state B minus the this new quantity, expectation value of position for sub AB, this weird quantity, and this is what you get after a bunch of algebra after algebra that I'm not showing. But this new quantity, this expectation value x sub AB, which looks kind of strange, is this. And you could find this out really easy just by going through the algebra, but I'm going to skip those steps. And it's going to be the integral of psi A star of x times the wave function b dx. And this we often call this we call the overlap, because this integral depends on the overlap between the two functions. Because you can kind of see from this integral that if I just plot the wave functions, like if this is psi and this is x, you can see that if I plot these two wave functions, if this was psi A and if this was psi B, then you can see that this integral, if the two wave functions did not overlap, the integral would be 0. But the more that the wave functions overlap, the bigger is that integral. So we often call this we often refer to this as an overlap integral. It depends on how much these two states overlap. And so you can see that this quantity x1, x2 sort of depends on the overlap of those individual states. So it's kind of an interesting quantity. And so then what we have then is that we see then that the distance between the two particles x1 minus x2 squared is equal to this quantity for the fermions. It's going to be, I'll write it all out, x squared A plus x squared for state B minus 2x A x expectation value of state position for state B plus 2 times this overlap integral AB quantity squared. All right, and so this is the distance for fermions. And so what I want you to see is that if I look at the symmetrized case, no symmetry, then we have this. And so this is, I want you to look at these two things. So you see here I have, this is with the unsymmetrized case, then we have this quantity. It's the x squared a, x squared b minus 2xa, xb. Whereas here, we have the same thing, x squared a, x squared b minus 2x squared xa, ab. This is the same. So this part is the same as the answer that we got for the unsymmetrized case. But now we have this extra part. Okay, so that's kind of a lot of work to get that, but it's all easy, you know, it's just trivial algebra, but it is kind of tedious. So now I will ask you a question. Let's see, unfortunately, I can't get these two things on the page at the same time, but I will now ask you the question. So suppose I have two particles in the same two states. There's no forces between them. They don't feel each other. But in one case, the particles are unsymmetrized. They're distinguishable, but in the other case, they're fermions. Is the distance between the two particles the same, or is it different? Now that's the question.
It should be different, shouldn't it?
Yeah, and for the fermions, and this is the case for the fermions, is the distance.
It will be farther apart.
Why farther?
Because the expectation and the expectation of the difference of the positions increases.
Well, I guess I would just say it's because this quantity is at magnitude squared. So this is a positive number.
Yeah.
That's what I want you to see. That's a positive number because it's a complicated quantity. It's this weird overlap integral. So it's hard to have an intuition for an overlap integral. But whatever it is, I'm taking the magnitude squared. And so whatever the hell it is, it's going to be positive. So that means that the distance is further apart. So the fermions are further apart than the unsymmetrized particles.
Professor?
Yeah.
But then, so is this true like all the time, or like does the overlap have to be like because could the overlap be 0 for fermions?
Yeah. So, you know, I could say that they're, you know, but in most cases there'll be some overlap, okay? You know, in most cases there'll be some overlap. I mean, you know, because the particles are all in the same system, they're in the same box, you know, so the wave functions will always have some non-zero overlap. So I think it's actually a pretty general result. And even though the particle, even though the states are orthogonal, so you might say, hey, the states are orthogonal, so the overlap should be 0 because they're orthogonal, right? Wrong. That would be wrong because I have this x here. All right, I have that x in the integral. So if that x was not there, then that integral would be 0 because these are orthogonal eigenstates. But because that x is there, it's not 0. Okay, so
Professor?
Yeah.
So states being orthogonal to each other doesn't mean that they are linearly independent? Or, I mean, so states being orthogonal means they are linearly independent, right? And then they are?
They are what?
No, there's no overlap.
Haha, that's actually not correct. Yeah, that was what I was just pointing. I'll just remind you, because I know you've seen this before. Here there's a bunch of states: state A, B, C, and state D. Right? These are the states, right? Okay, you know, the particle in a box states. Now these are orthogonal states, and what that means is that the integral of any two states, A star of x, B of x, dx equals 0. That's the definition of orthogonal. And linear independent is kind of something different. That just means, you know, that they form an orthonormal basis, and we don't need to get into that nuance. But this is the definition of orthogonal. But what I'm talking about is the overlaps, which is something totally different, because the overlap of states A and B would be psi star A of X, X psi B of X. And that might not be zero. It depends. You know, you sometimes it might be zero if you have odd, even. You know, you can play these little games of like, oh, is it an odd or even integral? But those are just nuances and details. The point is that in general, eigenstates, the overlap between eigenstates in general is not zero. Does that make sense, what I'm saying? Because I have this extra thing. Because of this.
Yeah. Okay.
All right. Because
yeah, when I just heard overlap between the states, I just imagined that there is some sort of yeah, it's just hard to imagine that, like, overlap being not just the overlap between the states, but there's a position. So overlap is overlap in position of the states?
Okay, yeah, so why don't we call it, we can call it the, instead we could call it the exchange overlap. How's that? Maybe I'm, yeah, I can see why it's confusing you, because, you know, people use the word overlap in a different context when they're just talking about this integral, what I'll call here integral number 1. I'm interested here in integral number 2, and I do appreciate that many people would call integral number 1 the overlap integral, and so I can see why that's confusing to you. So why don't I call it the exchange overlap? How's that?
Okay.
Okay, so it's just a definition. It's just, you know, it's just something that comes out of the algebra. You know, it's like this new quantity, this exchange overlap, which I'm calling this quantity AB. Okay, this XAB. Okay, and so then if we now let's go through this same algebra for bosons and do it all for bosons. And then what we're going to find is that for bosons, for the symmetric case, what we're going to find is that we get, let's see if I can get these both at the same time. Shoot. Yeah, maybe I can. Let's see. It'll be x1 minus x2 squared is equal to x squared a. After you go through all the algebra that I'm not going to do, x squared b minus 2 x a x b, but now it's going to be minus 2 x a b squared. And so this quantity now is negative. So on average, the two particles in a symmetric state, on average, are they further apart or closer together? That's my question.
Closer.
Yeah, they're closer. Because you see that this is the result that we got for the unsymmetrized case. And so you can see that for the symmetric bosons, the two particles are closer than you would get for the unsymmetrized case. Whereas for the fermions, they're further apart. So the difference between fermions and bosons is quite different. The particles for the fermions are further apart, and for the bosons, they tend to be closer together. And so for the bosons, they're closer together. And this has consequences. Let me tell you a consequence, because suppose I have two particles and we put them here in state A and B, and now we consider these two wave functions. On the one case, I have psi for the fermion case, I have psi is equal to, and I'll just 1 over square root of 2, I'll just call it psi A, psi B, minus psi B, psi A. I'm just trying to write it a little quicker because it's so tedious to write all that stuff. But for the bosons, I have psi is equal to 1 over square root of 2, psi A, psi B, plus psi B, psi A. Now, if there's no interactions, then the energy of this case is going to be energy of particle A, state A, plus energy of state B. And the energy here is going to be what? What's the energy of those two bosons?
Should be
EA
the
plus EB.
What?
EA plus EB again.
Exactly. So you can see that the energy is the same. Whether they're bosons or fermions, you know, how I symmetrize it, there's no difference between them. But now, let me ask you a question, and we're just about to end. Suppose now that the charges, suppose the particles have charge, like electrons. And so now they have the same charge, positive charge, let's say negative charge. Do the two states have different energies now? So now let's give the particles some charge so they can feel each other. So now I'm kind of breaking the rule. I'm saying that they can feel each other. And I'm asking you, is one of these states higher in energy than the other? Which one?
I think it would be the boson case because they would be closer together, so the distance is smaller. So the Coulomb, the potential would be larger for the boson.
That's exactly right. That's exactly right. Then this is, if they have charge, then the symmetric state is higher in energy, and the anti-symmetric state is lower in energy, That
Is it?
Huh?
Does this relate kind of like the weak and strong nuclear force? Is that?
I don't know. I don't know anything about the weak and strong nuclear force, but this is the origin of magnetism. So this is why we have ferromagnets. This is the origin of magnetism, and I'll explain why next time. But I will just stop here by saying this effect is the origin of magnetism. This is why we have magnets. This did not occur, we would not have magnets. So think about that, and we'll discuss why that is next time. Okay, bye-bye. Bye-bye.
Thank you.
Okay.
Thank you.
Okay.
Thank
bye-bye.
you.